In this lesson and in this series of lessons, we are going to talk about sorting algorithms. Sorting as a concept is deeply embedded in a lot of things that we do. It's quite often that we like to arrange things or data in certain order, sometimes to improve the readability of that data, at others to be able to search or extract some information quickly out of that data. For example, something as simple as when we are playing a card game, even though the number of cards in our hand is really less, we like to keep our hand of cards sorted by rank or suit. So let's say this is our hand of cards and we would like to keep it in increasing order of rank, then the arrangement will be something like this. Now have a look at this. When we go to a travel site to book a hotel, and then the site gives us all these options of sorting the hotels by price from low to high, or by star rating, or by guest rating. So right now I have my options sorted by guest rating, so the hotel with the highest guest rating is at the top. I may be on a budget and I may want to avail the cheapest option, so I would sort the hotels by price from low to high, and now the cheapest hotel will be at the top. And I may still try to strike a balance between rating and price. So sorting is a really helpful feature here. And there are so many places where we like to keep our data sorted. Be it a language dictionary where we want to keep the word sorted so that searching a word in the dictionary is easy, or something like a medal tally where we want to see which team is at the top and which team is not performing so well. If we want to define sorting formally, then sorting is arranging the elements in a list or collection in increasing or decreasing order of some property. The list should be homogeneous, that is, all the elements in the list should be of same type. To study sorting algorithms, most of the time we use a list of integers, and typically we sort the list of integers in increasing order of value. So if we have a list of integers like this, 2, 3, 9, 4, 6, then sorting it in increasing order of value will mean rearranging the elements like this. Sorting the list in decreasing order of value will mean something like this. And as we have said in the definition, we can sort on any property. What if we want to sort this list on the basis of, let's say, increasing number of factors? So the number with lesser number of factors is towards the beginning of the list. If you see, 2 has got only 2 factors, 1 and 2 itself. 3 has also got only 2 factors, 1 and 3 itself. 9 has got 3 factors, 1, 3 and 9 itself. 4 again has got 3 factors, 1, 2 and 4 itself. 6 has got 4 factors, 1, 2, 3 and 6 itself. A sorted list is a permutation of the original list. When we sort a list, we just rearrange the elements. Now this was a list of integers. We may have a list of any data type. We may want to sort a list of strings or words in lexicographical order, the order in which they will occur in dictionary. A list of strings like this in lexicographical order will be arranged in this order. And we may have a list of complex data type as well. A hotel object in the hotel list that we had seen earlier was a complex type. Hotel will have many properties, like its price, its distance from the city center, its guest rating, its star rating, and the list can be sorted on any of these properties. Sorted data is good not just for presentation or manual retrieval of information. Even when we are using computational power of machines, sorted data is really helpful. If a list is stored in computer's memory as unsorted, then to search something in this list, we will have to run linear search. In linear search, we start at the first element in the list and keep scanning the whole list until we get the element that we are looking for. So in the worst case, when an element will not be there in the list, we will compare it with all the elements in the list. We will scan the whole list. So if there are n elements in the list, we will make n comparisons in the worst case. And think about the kind of data that modern day computers deal with. What if this n is really large? If we take n equal 2 to the power 64 and imagine that one comparison takes 1 millisecond, then we will take 2 to the power 64 milliseconds. If you try to convert this to seconds, hours, days, and so on, this will amount to some years. If our list, however, is sorted, we can use something called binary search, And with binary search, if size of the list is equal to n, it will take only log of n to the base 2 comparisons to perform a search. So if n is equal to 2 to the power 64, we will take only 64 milliseconds. I had taken n equal 2 to the power 64 earlier to be able to perform this log quickly. Sorting as a problem is well studied, and a great deal of research has gone into devising efficient algorithms for sorting. In this series of lessons, we are going to study, analyze, and compare these sorting algorithms. Some of the sorting algorithms that we will be talking about, that we will be analyzing, are bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, counting sort, radix sort, and this is not all. There are more, and you can imagine how important sorting as a problem is. We have so many algorithms for sorting that have been designed over a period of time. We often classify sorting algorithms based on some parameters. The first parameter that we want to classify upon is time complexity, which is the measure of rate of growth of time taken by an algorithm with respect to input size. Some algorithms will be relatively faster than others. The second parameter that we use for classification is space complexity or memory usage. Some sorting algorithms are in place. They use constant amount of extra memory to rearrange the elements in the list, while some sorting algorithms like merge sort use extra memory to temporarily store data, and the memory usage grows with input size. The third parameter that we talk about is stability, and this one will take some explanation. Suppose we have a set of cards like this, and we want to sort these cards in increasing order of rank. We have 1 3 of diamond, we have 1 9 of spade, and we have 2 6s, one of club and another of heart. One possible permutation will be this. The cards are sorted by rank. We have got 3 6 6 9, but if you see in the original list, 6 of club was coming earlier than 6 of heart, but when we have this permutation, which is a sorted arrangement, 6 of heart, this particular card, has come before 6 of club. A stable sorting algorithm, in the case of equality of key or the property upon which we are sorting, preserves the relative order of elements. So if the key is equal, if an element was coming before in the original list, it will also come before in the sorted list. A stable sorting algorithm guarantees that. So if we will use stable sorting algorithm, we will get this particular permutation where 6 of club will be before 6 of heart. The next parameter of classification is whether a sort is internal sort or external sort. When all the records that need to be sorted are in main memory or RAM, then such sort is internal sort. And if the records are on auxiliary storage like disk and tapes, quite often because it's not possible to get all of them in the main memory in one go, then we call such a sort external sort. There is one more parameter upon which we may classify sorting algorithms, and it is whether the algorithm is recursive or non-recursive. Some sorting algorithms like quick sort and merge sort are recursive, while others like insertion sort and selection sort are non-recursive. We will study all these properties in detail as we will study these individual algorithms. This is it for a basic introduction. Thanks for watching.